Good morning to all of you.
Good morning, sir.
Good morning,
Good
sir.
morning, sir.
Good morning. Is my screen visible?
Yes, sir.
Yes, it is visible.
Sir,
Okay. So, are there any questions, doubts?
Sir, one doubt is there.
Yeah.
In plate bending, how
Yeah.
that dw that angle become dw by dx? Means from geometric point of view, how we can conclude that okay, this angle is dw by dx or
That
dw by
is
dy?
the slope of the deformed middle surface, no?
Sir, slope, uh, but I can understand actually how they taking slopes means.
Tangent
Uh,
is rotating. See, when you have a curve now, the W is a function of X and Y, and the slope would be del W by del X. So tangent is rotating by del W by del X, and normal will also rotate by del W by del X.
oh, dw. Yeah,
Slope
yes,
of the curve basically. So
yes,
slope
yes.
of the curve is rotation of the tangent, and then normal will because normal remains normal after deformation. So rotation of the normal will also be del W by del X. And
Del X.
similarly, in the other plane, it would be del W by del Y.
Okay, okay.
So are there any other questions?
Hello, sir.
Yeah,
So this the derivation which we have done for classical plate bending element, so it is
yeah,
valid for only small deformations, right?
right, right. Yeah, it is valid for small deformations.
Sir, how can we categorize a problem into small and large deformation? Like, if
Yeah,
we will face any practical problem, how we can say
yeah.
what is
So
the
if
criteria?
yeah, so you look at W by H. But W is, let's say, the maximum displacement to thickness ratio. If that is no approaching to unity, say zero point 0.5, zero point 0.6, 0.81, then it would be a large deformation problem. But if W by H is much less than unity, say W by H is zero point 0.1, zero point 0.2, or zero point 0.01, and so on, then it would be a small deformation problem. So it is based on the values of W by H, where W is the maximum displacement to thickness ratio.
Okay, so
Okay? Yeah.
Hello.
Yeah.
Sir, to add on to this question only,
Yeah.
so basically you are telling us that we should find W by H to
Yeah.
decide the deformation, right? Will if
Hmm.
it will be big or small. But sir,
Yeah.
that W in general cases, like whenever we will be working on a problem, that
Yeah.
will be calculated by us. Like
Yeah.
it will not be from practical or experimental data, right?
Yeah. Yeah. It
So,
is from
so
the calculation.
okay, so first we will have to. So the process will be like first we will have to assume that the deformation is small and we will
Yeah.
calculate everything, and from
Yeah.
there if we find that w by h is tending to 1,
Yeah.
so in that case we will have to do one more iteration for larger deformation. Is it like
Yeah.
that, sir?
Yeah. Then yeah. Right. Exactly right. So first you do a linear analysis.
Okay.
So assuming that the deformations are small, so only linear strain displacement relations, and then you get the W, and then you find out W by H. If it is approaching to 1, then you do a nonlinear analysis, including the quadratic terms in the strain displacement relations.
Okay, sir.
And when you are going for a large deformation, then the middle surface will also stretch. So you'll have to also include the displacements of the middle surface. So you will have displacements like U naught minus Z into del W by del X, and V will be V naught
Oh,
minus Z into del W by del Y. And then the strain displacement relations, you take the quadratic terms also.
okay, sir.
Yeah.
Sir, in the total potential energy functional integration form, that is
Yeah.
d omega by dn transpose into mn. Sir, what is mn? Mn equals to mx, my.
M is
This
the moment per unit length on a
which
plane
moment?
having outward normal along X, along N, outward normal along N. So there would be on the boundaries, now there would be transverse force that we are denoting by Vn, capital Vn, and there would be moment on the boundary. The moment would be about tangent to the boundary, so that we are denoting as Mn. So these are the two contributions from the boundary tractions and moments.
Hello, sir.
Yeah,
Sir, actually, you told the example of mxy on which tau xy is acting on positive x surface.
yeah.
What if it is acting on negative surface?
So
Then
then
what
you
will be
can
the
accordingly decide the direction, whatever moment it gives. So say what I had explained was, okay, it is not writing, so let me close the file and open it. Yeah, so what I had told is, if you remember, so I had told mxy. So suppose these are the coordinate directions. So this is x, and this is y, this is z. If it is on the negative phase, so you still take on the positive z side. So say this point. So here your this will be sigma xx, and tau xy would be this. So tau xy, and because of this, see, the sigma xx will produce the moment about no negative y axis. So mx here would be like this. So this would be mx, and tau xy, if you look at, it would be a moment like this. So that would be moment about positive x-axis. So on the negative x phase, mx, the moment resultant mx would be about negative y-axis, and mxy would be the moment about positive x-axis. So like that, you based on the positive sign convention for sigma xx and tau xy. So is that clear?
yes, sir. Thank you.
Hello. Yeah. So are there any other questions? Okay, so if there are no questions, let me start. So last class we were talking about this four noded rectangular element with 3 degrees of freedom at each node. 3 noded rectangular element. And so the element was like this. So we have 4 nodes in the element. This is z axis, this is x. So this is node 1, 2, 3 and 4. The coordinates are 0 comma 0, a comma 0, a comma b, and this is 0 comma b. The degrees of freedom at these nodes are w1, because we said primary variables should be degrees of freedom at the node point. So del w by del x at 1, del w by del y at 1, then w2, del w by del x at 2, del w by del y at 2. Similarly at node 3 and 4. So now like this, each node we have 3 degrees of freedom, the deflection w, transverse displacement w, the rotation del w by del x, and del w by del y. So there are 4 nodes, so there will be total 12 degrees of elemental degrees of freedom. So whatever approximate solution we assume, it should have 12 terms. So we said that approximate solution for this element, so we have w, which is a function of x and y. So w is equal to a0 plus a1x plus a2y plus a3 x square plus a4 xy plus a5 y square plus a6 x cube plus a7 x square y plus a8 xy square plus a9 y cube plus a10 x cube y plus a11 x y cube. So this is the solution based on the Pascal triangle I had discussed. So we get this as a solution. Now, so this is where we stopped in the last class. Now we wanted to check compatibility. So now let us see whether this element is compatible or incompatible. So to check that, we consider the assembly of elements. So let me take a simple case, assembly of two elements. So element 1, element 2, element 3 and 4, and these are the nodes. And let us say if we take the common boundary AB, which is common between element 1 and 2. So if you look at along line AB, we have x is equal to constant. So this is x and this is y. So x is equal to c, which is a constant. For both the elements 1 and 2 along AB, x is constant, some constant. So now if you put in this expression of the approximate solution for W, x is equal to constant, you will get W is equal to, if you take all the constant terms together, you will have A naught plus A1 into C plus A3 into C square plus A6 into C cube. So these will be the constant terms, then terms linear in y. So that would be a2 plus a4 into c plus a7 into c square and plus a10 into c cube into y. So what I am doing in this expression, I am putting x is equal to constant and then collecting all the constant terms, the terms linear in y, terms quadratic in y, and terms cubic in y. So plus you will have a5 plus a8 into c y square plus we will have a9 plus a11 into c into y cube. So you can say that now this first is some constant. So let us say a0 plus capital A1y plus a2y square plus a3 y cube. So this is the W along line AB. W would be varying as per this along line AB. Now if you, what you can do is you differentiate this expression with respect to y and then again put x is equal to 0. So you will get del W by del y will come out as you can see from that it would be A1 plus twice of A2y plus thrice of A3y square. So this is how you will get del W by del Y. Now if you look at, we need to look at, because now W del W by del X and del W by del Y are primary variable. So we'll have to look at all of these. Then del W by del X along same line AB. So what you have to do again, now in this expression, first you differentiate with respect to x and then put x is equal to constant. So you will find that del W by del X will come out to be some a1 plus and then collect all the constant terms together plus 3a3 c square plus a4 plus 2a7c plus 3 a10 c square into y plus a8 into y square plus a11 into y cube. So this is what you will get as del W by del X along line AB where X is constant. And you will see, now see here now in the W and del W by del Y, these constants are same. This is same what you have here, this is same what you have here. But you will see that these constants are different. They are not same as a0, a1, a2, a3. So these constants are, let us say, some b0 plus b1y plus b2y square plus b3y cube. So these are different set of constants. Now when you look at along line AB, at A and B we already have w del w by del x and del w by del y common in both element 1 and 2. That means at node A, element 1 and 2 have same w del w by del x and del w by del y. Similarly, at node B, both elements 1 and 2 have same value of w del w by del x and del w by del y. So now if we look at now from these two, w and del w by del y, so they are in terms of w as well as del w by del y, are in terms of these are the cubic, del w is a cubic polynomial and del w by del y is a quadratic polynomial, and they are involving four constants a0, a1, a2, a3. So at A we have common values of w and del w by del y, and also at B we have common values of w and del w by del y. So in between, when we fit this cubic curve, so we will get the same variation of w and del w by del y along line AB from element 1 and 2, because these four constants will be expressed in terms of same values of w and del w by del y at node A and B for element 1 and 2. So you will see that these will be same. These means w and del w by del y will be same along AB from element 1 and 2. But now if you look at del w by del x, so del w by del x is also cubic in y, it involves four constants. But now we are left with only common values of del w by del x at A and common values of w and common values of del w by del x at B. So we have only two common values, that is del w by del x at A and B, whereas there are four constants. So this will not be same. Del w by del x will not be same along line AB from element 1 and 2.
Hello, sir.
Yeah,
Sir, AB node has two means two node. AB element has two nodes, and but W and DW and DY means approximate what we have done. It is a quadratic or means 3-degree
yes,
polynomial.
w
Then how
w
can
is cubic along AB. No, see if you look at w is cubic along AB, cubic in y, and del w by del y is just the derivative of that, so that is quadratic in y. So, but both w and del w by del y involve same constant a0, a1, a2, a3. So these four constants can be determined from the four values of w del w by del y at A and w and del w by del y at B. Since the value of w and del w by del y are same at A and B from both the elements 1 and 2, so this function will turn out to be same whether we get it from element 1 or 2. So that is how I am saying that these, that is w and del w by del y, will be same along AB whether we calculate it from element 1 or element 2.
yes, yes, sir, yes. But sir, variation is means 3-degree polynomial. Then
Yeah,
how
yeah.
we can compare between 2 point?
So because at two now if it was only value of w, then it is not possible. But 2 points, but at each point we have w and this del w by del y. So these are four values, no, w and del w by del y at A, w and del w by del y at B. So these are four values. So we are not just taking w, we are also taking del w by del y. That is why I am saying that no, these are four values, so we can find out the constants a0, a1, a2, a3 from both the elements 1 and 2. They will be same constants. That is how I am saying that w and del w by del y would be continuous across elements along line AB.
Okay.
Yeah. But when you look at del w by del x, that is also cubic and it involves four constants. But now we are left with only del w by del x at A and B. So these are only two values. Whereas now we have four constants. So we cannot get the unique variation of del W by del X along AB from element 1 and 2. In general, at A and B, del W by del X from element 1 and 2 would be same, but in between del W by del X from element 1 would be different from del W by del X from element 2. So that is why this will not be continuous across AB from element 1 and 2. So that means you see what we are concluding here, that W and del W by del Y are continuous along AB, but del W by del X is not continuous. So we are seeing here that W del W by del Y continuous along AB, but del W by del X is not continuous. When we say along AB, so yeah, it's actually across the elements. Now, if you are talking about it is across elements, continuous along AB, but del W by del X is not continuous.
Continuous or compatible?
Yeah, continuous means across elements 1 and 2. So we are of course talking about compatibility. Compatibility means continuity of W del W by del X and del W by del Y along line AB when we calculate from element 1 or 2. So when we go from element 1 to 2, at the same point we should get same values. So then it is compatible. If we are not getting same values, then it is incompatible. So I'm saying del W by del Y, del W and del W by del Y are continuous along AB, but del W by del X is not continuous across elements 1 and 2. So if you are talking about element 1 itself from A to B, all are continuous only, but when we are talking of this continuity is across the elements. That is when we take line AB in element 1, when we take line in, AB in element 2 and calculate these values. If they are same, so that's what I'm saying continuous. And if it is not same, then I'm saying that this is not continuous. So that means this element is incompatible element because all the primary variables are not continuous across the element. So this is incompatible element. So now similarly, if you take a line element having say y equal to constant, let us say line BC between element 2 and 4. So now if you take say along line BC, so in similar logic, now if you extend, you can say that similarly along line BC and along line BC will have y equal to constant. So you will actually find that along BC W and del W by del X will be continuous, but del W by del Y will not be continuous. Will not be continuous across elements now we have elements there is 2 and 4. So now the conclusion is that when we are moving along a line with x is equal to constant, W and del W by del Y will be continuous, del W by del X will be discontinuous. And when we are moving along a line with y equal to constant, W and del W by del X will be continuous across the elements, but del W by del Y will not be continuous. So that is the conclusion. So you can say that W is continuous, of course, whether it is a line with x equal to constant or line with y equal to constant. But as far as the derivatives are concerned, so the derivative along normal will be continuous, derivative along tangent would be discontinuous. So like here, if you look at line AB, the normal is along x. So the del W by del Y is actually the rotation about normal, that is x. So that is continuous. But the del W by del X, which is the rotation about tangent to this boundary, that is this line, that is not continuous. Similarly, when you take line along BC, W is continuous and the del W by del x is continuous. Del w by del x would be rotation about normal. Normal on this boundary is along y. So the rotation about this normal is continuous, but the rotation about the tangent, that is x-axis, is discontinuous. So that is the conclusion here. So in a you can say that W is continuous across the elements, continuous across the elements, and rotation about normal to the edge, normal to the edge, to an edge. I think let me not say and rotation about normal to an edge is continuous, but rotation about tangent to an edge is not continuous. Continuous across elements. Across elements. So this is the conclusion from this. And now, what is the problem with the incompatible elements? So the incompatible elements do not depict monotonic convergence. So incompatible elements do not depict monotonic convergence. So what it actually means is that when we do the convergence study, that means if we increase the number of elements and plot, say, the displacement at the center of the plate. So this side, let us say we have WC, that is W at center, and this side we have number of elements. So that is, we keep on increasing the number of elements. So now if we now we will have some exact solution. So let us say exact solution is somewhere here, which is constant. So this is the exact solution. And now when we have, if we have actually a compatible element, the compatible element will depict a monotonic convergence. That means we will start some with some s, and we will get some W values, and when we keep on increasing the number of elements, W would increase and finally tend to the exact solution. But if it is if the element is incompatible, so that will give you no oscillatory convergence. So you may get the convergence curve may turn out to be something like this. So you will see that this is monotonic convergence. This is monotonic convergence from compatible elements, if the element is compatible. And this is one, if you see, this is non-monotonic convergence. So it is not non-monotonic convergence, or you can say it is oscillatory. It is oscillatory convergence. This comes from the incompatible element. So this is the so the problem is because in case of monotonic convergence, we know that if the two consecutive meshes have got almost the same value of W, then it is converged. But in oscillatory convergence or non-monotonic convergence, let us say our starting mesh is somewhere here, and our the next mesh gives you this result. So B might wrongly conclude that these two values are nearly same, whereas no, the exact solution is lying somewhere here. So B will just think that these two are nearly same, so we have got the converged result, but there is so much of difference from the exact solution. So it is difficult to ascertain convergence in case of incompatible elements. Although of course, if you keep on refining, you even if you get the same values, you do the further refinement, so you will be able to get to that. But usually, you would require large number of elements to get the converged solution close to exact solution for from the incompatible elements. So that is the problem with the incompatible elements. So but yeah, this is what we have. Sometimes we still use incompatible elements because this is simple in the sense that we have 3 degrees of freedom at each node which have physical meaning, that is deflection w and the rotation about del w by del x, rotation about y, and del w by del y, rotation about x. So that's a simple element, and we do use that element. So am I audible?
Yes, sir. Sir,
Yeah.
so does it mean for large number of elements, the this non-monotonic convergence will mean that the solution will kind of oscillate about the exact solution?
Yeah, for large number of elements, it might see if you have very large number of elements, then that oscillation amplitude would be very less. So you can say that there you will get converged values, but usually number of elements required from the incompatible no number of incompatible elements would in general be required much more than the number of compatible elements to get the accurate solution.
Okay.
Yeah.
So this oscillation has been considered by taking different number of elements, right?
Yeah, yeah.
Means
See,
one
one
study we
side
are
you have,
doing with.
yeah, different number of elements. That's what, no, x-axis is number of elements, as you see here.
Okay, sir.
Yeah.
Sir,
So
one
then,
doubt.
yeah, yeah,
Sir, then how do we know that when to break out of loop for non-monotonic convergence? Like,
yeah. So now
is there
usually
any?
monotonic convergence, if two consecutive meshes are giving almost the same result, then you stop there. But in non-monotonic convergence, you have to look at even if two consecutive meshes are giving same result, you have to go for still more number of elements and check whether you are getting the same results. So if say 3 consecutive meshes are giving almost the same result, then you stop there in case of non-monotonic convergence.
Okay.
Yeah. So now once we have discussed about this, so now rest of the things are about the development of element level governing equations. So now we have these 12 constants A0 to A11. So we need to express these constant in terms of the elemental degrees of freedom. So we know that at first node we have no this is the element, and these are the nodes 1, 2, 3, and 4, and these are the coordinate axes. So this is 0 comma 0, this is a comma 0, this is a comma b, and this is b 0 comma b. So now if you say w is equal to w1 at node 1, so in at node 1 x and y are 0, so you will get w1 is equal to a naught, and then del w by del x. So first you differentiate the expression for w and then put x equal to 0 in that, so you will get del w by del x at node 1 will be equal to a1, and similarly differentiate expression for w with respect to y and then put x and y equal to 0, so you will get del w by del y at node 1 as a2. And then if you look at w2, so in the expression for w, if you put x is equal to a and y equal to 0, you will get w2 as a0 plus a1 into a plus a3 into a square and plus a6 into a cube, and then you will get del w by del x at 2. So first differentiate the expression for w with respect to x, and then put x is equal to a and y equal to 0. You will get this as a1 plus 2 a3 into a plus 3 a6 into a square. And similarly, no, del w by del y at node 2. So differentiate w with respect to y and then put x equal to 0 and x equal to a and y equal to 0. We'll get this as a2 plus a4 into a plus a7 into a square plus a10 into a cube. And so similarly, you can write all the degrees of freedom. So same way, you will have W3 expression for W3 del W by del X at 3, del W by del Y at 3, then W4 del W by del X at 4. So you can write all of these and then you can set up the equations. So if you want to write the relationship between the elemental degrees of freedom and the unknown constants A0 up to A11 in terms of matrix vector, so this relationship can be written something like this. So we have a matrix here, and then these constants A0, A1, A2, A3, A4, A5, A6, and A11 finally. And this will be equal to vector of elemental degrees of freedom. So that is W1 del W by del X at 1, del W by del Y at 1, W2 del W by del X at 2, and so on. Finally, we'll have del W by del Y at 4. So you will have this kind of a relationship. So if you see the W1 is nothing but A naught, so there we will have a 1 and then 0, 0, 0, 0, 0. So these are 11 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah. And then del W by del X at 1 is A1. So that you can write 0, 1 and then these zeros. Then if you look at del W by del Y, that is equal to A2. So that would be 0, 0, 1 and then these zeros. And then you have W2. W2 is no, W2 I have written, this is the expression for W2. So same thing if you want to put in this matrix form. So that would be 1, A, 0, A square, 0, 0, then A cube, then these zeros. Then del W by del X at 2 would be 0, 1, 0, 2A, 0, 0, 3A square. Then if you look at del W by del Y at node 2, so that would be 0, 0, 1, 0, A, 0, 0, A square, then 0, 0, A cube and 0. So like that, you can write all the degrees of freedom like this. You will be able to write all of these. So now we can write actually, this if I denote as a capital matrix A, and this has the constant A, and the right hand side what we have is the vector of elemental degrees of freedom. So this matrix is A, this is small a,
Hello,
and this
sir.
is D. Yeah,
Sir, if this approximate solution is not compatible, then
yeah.
I mean, then why you are doing these calculations for shape functions? Means why we are calculating these constant terms? Because
Yeah,
this
so
is
it
not
is,
solution.
yeah, it is not compatible, but this element is simple. So still sometimes we use this element. So it is not that it is not at all used. Of course, you have to, when you are using this element, you have to ascertain the convergence properly. But this element is also used. So that is why we are discussing, we want to formulate it. The advantage is that at nodes we have the degrees of freedom which are physically interpretable as geometric quantities, deflection and rotations. So this element is actually still used. That is why I am discussing the further development of this element.
Okay, sir. Means in any means if we are comfortable, then we can use element which are not compatible also.
Yeah, we
If we
can.
can interpret the primary variable easily.
Yeah, yeah.
Okay.
So now, see, now in this case, you would be able to write this vector of constants, unknown constants, as A inverse into D, vector of elemental degrees of freedom. So then you
Sir,
can write
can you
W.
scroll
Yeah,
upward
yeah,
slightly?
yeah. Hmm.
Sir, can you scroll? Yes, sir.
Yeah.
Sir, actually, I was noting the matrix. I was unable to note it.
Yeah. So
Yes, sir.
I'm
Now
going
you
to
can.
upload. I'm going to upload this solution anyway, so you can look at it. No.
Okay, sir.
Yeah, I'm going to I upload this now in the Imparters backpack. So along with video, you also have this under backpack. You can see, these notes. So
Okay,
you will
sir.
see W will be equal to, now we write in terms of the variables, xy. So 1 xy, x square, xy, y square, and then we will have x cube and so on. And then finally last term would be xy cube into these constants a0, a1, a2, a3, a11. So you can see that this will be equal to 1 xy x squared xy cube, and this vector will be A inverse into DE. You will see that this is 1 by 16. A is 1 by 12, not 16. 1 by 12, and this is 12 by 12, and this is 12 by 1. So finally the shape functions would be 12 row vector with 12 columns. So you can say that W would be equal to n1, n2, n3. So like that you multiply here n12 into DE. So we call this as the interpolation matrix. So this is H into DE. So see, when if you develop a MATLAB code, so you can form the complete A matrix and then multiply, the take its inverse, and then pre-multiplied with this 1xy, you will get the 12 shape functions. So the where H is the interpolation matrix. That notation we have already used. Then now see, if you look at, if we want to finally substitute this approximate solution in the integral functional, so we also need the second derivatives of W with respect to x and y. So that vector we call as a curvature tensor. So the curvature kappa, I'm denoting that by curvature kappa. So this will be equal to del 2 W by del x square, del 2 W by del y square, and twice of del 2 W by del x del y. This can be written as, so you have this matrix over here, and this side you will have DE, vector of elemental degrees of freedom. So this side, because W is the in terms of n1, n2 up to n12, so you have simply the derivatives of those. So here we'll have del n1 by del x square, del 2 n2 by del x square, del 2 n3 by del x square, and so on. Finally, we'll have del 2 n12 by del x square. Similarly, for del 2 W by del y square, you will have del 2 n1 by del y square, del 2 n2 by del y square, del 2 n3 by del y square, and del 2 n12 by del y square. And this will be twice of del 2 n1 del x del y, twice of del 2 n2 del x del y, and so on, twice of del 2 n12 by del x del y. So we call now this as, we can say that curvature vector kappa will be equal to some b into dE. So this we are calling as b. and this is the curvature. So curvature means del 2 w by del x square, del 2 w by del y square, and twice of del 2 w by del x del y, that is curvature. We also need in the integral functional the derivative with respect to normal n. So we will have del w by del n, and the normal could be either x or y. In general, del w by del n would be nx into del by del x plus ny into del by del y. So del w by del n would be similarly will be equal to del n1 by del n, del n2 by del n, del n3 by del n, and you will have into dE. You will note here that when we get these shape functions, so see n1, n2, n3 would be corresponding to node 1, n4, n5, n6 would be corresponding to node 2, n7, n8, and n9 would be corresponding to node 3, and n10, 11, and 12 would be corresponding to node 4. So that you should know. No, and this, let us say this we call as hn, derivative with respect to n as hn into dE. So this is your hn. Now if you look at the integral functional which we had written in the last class, so the integral functional is I is equal to, we will have half integration over area, and then no, the integral functional you can write in terms of this kappa transpose into matrix D. This is I am putting as matrix D into kappa dA. We have already written, so only thing is I'm using these notations. Minus you have integration over area W transpose into QdA, minus we have this boundary integral W transpose into Vn plus del W by del N transpose into. So now you can see here, now let me first define here. So these some of the quantities are not defined. So where kappa I have already defined, but if you look at your matrix D is D nu D 0, nu D D 0, 0 0, 1 minus nu by 2 into D. So this is your D. Other variables are already defined. So now with this you can say I will be equal to kappa is equal to B into D. So kappa transpose would be D transpose into B transpose. So that you can write half D, you can take out of the integration sign. So we'll have D transpose, and then a matrix which is in terms of integral A, we will have B transpose into matrix D into B into dA into dE minus, so minus we will have dE transpose integration over area W is equal to H into D. So W transpose would be D transpose into H transpose. So we will have H transpose into QdA, and then again minus we will have this DE transpose integration over line, and then we will have H transpose into Vn plus Hn transpose into Mn ds. So now let us say the various matrices. So this matrix what we have here, we call it as element level stiffness matrix. So let us say that is Ke, and this is, let me denote it as the external load vector. So F external for the element. When we are talking of the element, this would be, this integral would be internal force because it is in terms of boundary traction and traction moment. So that is F internal. So you can say that I will be half of dE transpose into Ke. K is the element level stiffness matrix. D, I am using the same notation what I used for 1D, so you can understand their meaning. So D transpose into F external for the element, and minus we will have D transpose into F internal for the element. So this is your I. So here I have already defined that K is integral A B transpose dB dA, and F external is integral A over area H transpose Q dA, and F internal is integration over the boundary H transpose Vn plus Hn transpose Mn ds. So that is F internal. So now for equilibrium, as we know, for equilibrium delta I equal to 0. So the logic is same. This will give you the element level governing equations as Ke into dE is equal to F external for the element plus F internal for the element. So this is the element level governing equation for this element. You will see that this would be 12 by 12. This is vector 12 by 1, 12 by 1, 12 by 1. So the B transpose is 12 by 3 into 3 by 3 D, and then B is 3 by 12. So you get K as 12 by 12. So that's the stiffness matrix. Now I give you a problem. So I will be actually asking you to submit as an assignment in grade scope. So but you can start working on this. So let me give you a problem that you have a plate which is discretized into 4 elements. It's a square plate discretized into 4 elements. So element 1, 2, 3 and 4, and these are the global node numbers 1, 2, 3, 4. So these are nodes, global nodes 1, 2, 3, 4, 5, 6, 7, 8 and 9. So you discretize this using 4 incompatible elements, that is rectangular element with 4 degrees of freedom. The dimensions are 2 meter by 2 meter, and the Young's modulus is, let us say, 210 gigapascals. Poisson's ratio is 0.3, and Q is a distributed force is, let us say, 10 pascals, and the thickness of the plate H is 0.001 meters. So the boundary conditions are, let us say, all the edges are fixed. So all the edges are fixed. All the edges are fixed. So you have to find out the deflection and rotation at node 5 for the plate, for the whole plate. So you have to discretize into 4 elements, and each element is a square element with sides as 1 meter, 1 meter. For each you can use a local coordinate system. So finally, for the solution of W, del W by del X and del W by del Y at node 5, you would require the 3 by 3 assembled matrix after eliminating the degrees of freedom at node 1, 2, 3, 4, 6, 7, 8 and 9. So you have to assemble only those. So finally find, so in this you have to find W5 del W by del X at 5 and del W by del Y at 5. So this is going to be your assignment. I will be formally uploading this assignment in the grade scope, and then you will have to submit within a, so I'll give you some time. I will maybe give 2 weeks or so. You can use MATLAB for doing all the calculations, and but of course in the when you upload the solution, you have to write all the steps and your MATLAB code you have to upload in that. So yeah, now yeah, I think I have some time. Yeah. So this is so far what we discussed is incompatible element. So can we have a compatible element? Yeah, is there any question? Okay. So now let me talk of a compatible element, although a rectangular compatible element. So rectangular, four noded rectangular compatible element. So now for this, what I'm saying is that you take a rectangular element with 4 nodes, but we increase the degrees of freedom. So local coordinate is x here, and this is y, and this is node 1, node 2, node 3, and node 4. The coordinates are 0 comma 0, a comma 0, a comma b, and 0 comma b. The degrees of freedom for this case, to have a compatible element, we need an additional degree of freedom. So we will have w del w by del x at 1, del w by del y at 1, and also we will have del 2 w by del x del y also as an additional degree of freedom. Although del 2 w by del x del y is not a primary variable, this is actually a secondary variable, part of a secondary variable. But if we have this also as the degree of freedom, then we can ensure the continuity of w del w by del x del w by del y across the elements. So that is why we introduce this. So similarly at node 2, 3 and 4, you will have w del w by del x at node 2, del w by del y at node 2, and del 2 w by del x del y at node 2. So these will be your degrees of freedom. So now if you see at each node we have 4 degrees of freedom, and there are 4 nodes, so their total elemental degrees of freedom would be 16. So when we assume an approximate solution, we take basically a polynomial with 16 terms. So when you look at the approximate solution, so we will have 16 terms. So for that, now when you look at the Pascal's triangle, so let us say I have Pascal's triangle 1 xy, then x square xy, y square, x cube, x square y, xy square, y cube, x power 4, x cube y, x square y square, x y cube, y power 4, then x power 5, x 4y. I'm just showing you the Pascal's triangle. Then x cube y square, x square y cube, then x y power 4, y power 5. Then we will have x6, x5y, x4y square, x cube y cube, x square y power 4, x y power 5, and y power 6. So for this, no, we take, this is 6. So for this, no, we take a bicubic polynomial. So we take all these terms which are inside this trapezium. So you take actually these terms in the approximate solution. So then the approximate solution W will be a0 plus a1x plus a2y plus a3x square plus a4xy plus a5y square plus a6x cube plus a7x square y plus a8xy square plus a9y cube plus a10 x cube y plus a11 x square y square plus a12 x y cube plus a13 x cube y square plus a14 x square y cube and plus a15 x cube y cube. So this will be your approximate solution. It has 16 terms corresponding to 16 elemental degrees of freedom. At each node we have w del w by del x, del w by del y, and del 2 w by del x del y as degrees of freedom. So these are the 16 terms, and now we want to check the compatibility. So if you want to check the compatibility, so again you need to consider an assembly of elements. So you can have any number of elements, but to demonstrate the assembly I am taking assembly of two elements. So this is element 1, this is element 2, this is element 3, this is element 4, and then again you take the same set of lines. Say, let us say here there are no A and B across the element 1 and 2, and B and C across the element 2 and 4. So now in this case, now the same logic which we discussed for the incompatible element, you can see that along line AB, x will be constant, x is equal to a constant, and you would be able to see now we have at A and B in both elements 1 and 2, w del w by del x, del w by del y, and del 2 w by del x del y common. So at an A and B, all these four values are same in element 1 and 2, and then in between we want to look at these. So along this line, if you see w, you can write in a similar manner the way we discussed. We will have w is equal to a0 plus a1y plus a2y square plus a3y cube, and del w by del y along line AB will be a1 plus 2 a2y plus 3 a3y square. So you will see that these are four constants. W and del w by del y are written in terms of four constants a0, a1, a2, a3. And now we can find out these constants a0, a1, a2, a3 in terms of values of w and del w by del y at a and b. Two values at a, two values at b, so four values. And those values are same for element 1 and 2. So we will get same set of constants a0, a1, a2, a3 from element 1 as well as element 2. So therefore we will get the same variation of w and del w by del y, whether we move along line AB in element 1 or we move along line AB in element 2. So that means these will be continuous across elements 1 and 2. So similarly, if you look at del w by del x, del w by del x will be some, you can see another set of constants. That is, now first we differentiate this expression now with respect to x, and then put x is equal to constant. So you'll get that as b0 plus b1y so you will get it as b0 plus b1y plus b2y square plus b3y cube. And if you look at this del 2 w by del x del y, so you will find this will turn out to be b1 plus 2 b2y plus 3 b3y square. So again you will see that we w del w by del x and del 2 w by del x del y are governed by four constants b0, b1, b2, b3. So we need four values, no? So at a and b we have del w by del x and del 2 w by del x del y are available with us. See, w and del w by del y are used for finding constants a0 and a1, a2, a3, and this del w by del x and del 2 w by del x del y at a and b will be used for finding out the constants b0, b1, b2, and b3. And since the values of del w by del x and del 2 w by del x del y are same at a from no element 1 or element 2, similarly they are same from element 1 and 2 at b. So we will get same constants from element 1 as well as same constants from element 2. So that means del w by del x and del 2 w by del x del y would be continuous along AB. So you can finally conclude from this that w del w by del x, del w by del y, and del 2 w by del x del y will be continuous along AB across elements 1 and 2. So, and similarly, if you similar logic if you extend, you can look at the along line BC also, you will get similar arguments, and so you would see that this element will satisfy the compatibility requirement. So all the primary variables will be continuous across the elements. In addition, of course, del 2 w by del x del y will also be continuous. Only problem with this element is that it has an additional degree of freedom which is not a geometric quantity. Like w del w by del x and del w by del y, these are geometric quantities, deflection and rotations. but del 2 w by del x del y is a secondary variable for the problem. This is actually twisting moment. So no, sometimes when we implement the no boundary condition, so it becomes difficult to interpret this. So now but this element is a compatible element and will depict monotonic convergence. So that is the advantage of this element. So I think no, I want to stop here, and we will continue the subsequent formulation of this element in the next class. If you have any doubts and questions, you can ask.
Sir, can't we go for any natural coordinates as we did in the case of coordinate
Yeah,
and
so you will find that we can go for the natural coordinates, but you will again find the because the derivatives are involved. So if you want to have the continuity of w and del w by del x, you need to have the degrees of freedom in the natural coordinate also. Del 2 w by del x square, del 2 w by del y square, and del 2 w by del x del y. In addition to these primary variables. So when the derivatives are involved, the situation is actually different. Sandeep, I'm in a class actually. I will call you back. Yeah. Yeah, so we can go for the natural coordinate formulation, but in the natural coordinate formulation also, because the derivatives are involved. So we have seen that if we have natural coordinate formulation and only the if the derivatives are not involved, then we can get a compatible element easily. But if the primary variables are derivatives of the variables also, then it is not easier. So now same thing when I will talk about the Mendelian plate theory, that is first order shear deformable plate theory. In that I will show you that when you use natural coordinate formulation, you get the incompatible elements, because there the primary variables are only variables but not their derivatives. So I will be demonstrating that. Yeah, any other question, anybody? Hello, anybody has any other question?
Sir, one
Yeah,
question. Sir,
yeah,
here we have taken dw by del x del y, del 2 w by del
yeah,
x del y, right?
yeah, right.
So this is like gamma xy by minus 2z, right? Uh,
Yeah,
but
yeah,
sir,
yeah,
while implementing this boundary, how will we like know that what is the gamma at that point? Because the at the same point,
yeah,
like
yeah. So,
primary
yeah,
variable and subsequent secondary variable cannot be defined.
yeah, yeah. So, yeah, corresponding secondary variable cannot be defined. So that is the difficulty. So usually, what if we have the only primary variables as degrees of freedom, then it is easy to give the boundary condition. But if the secondary variables are involved, then defining the boundary condition becomes a difficult task. Usually, what we do is specify only the primary variables and leave the secondary variables as unknown. So that is what we do actually.
Okay.
Yeah, yeah. So anybody, any other question?
Sir, we need to solve that assignment using incompatible.
Yeah, yeah, yeah. You have to using 2 by 2 mesh, and you have to do in MATLAB, because all the matrix and all know A inverse, then step functions, and then finding out the integration of B transpose D into B and all you can do using MATLAB.
And sir, the
And then you have to, yeah, pardon.
so the convergence condition we will use will be that if three consecutive mesh has same displacement value,
Yes,
then we will.
I'm going to ask you report the solution for 2 by 2 mesh. But if you want to do further, you can yeah, actually check if you go for 4 by 4 mesh or 6 by 6 mesh, what is the result?
Okay.
Yeah, yeah. Any other question? Anybody? So if there are no questions, I am stopping here. Of course, for this compatible element, you try developing the element level governing equations. So you should try developing the element level governing equations for this element yourself, although I will discuss in the next class. So thank you all for your attention. I am stopping.